Video, we will introduce all the terminology used regarding boundary conditions and initial conditions for partial differential equations. There are a lot of terms that are going to be involved with boundary conditions, so I really suggest you take some good notes during this video so you can remember all these terms and what they mean as we use them in the future. So, for a concrete example, we are going to be using the heat equation throughout this discussion. So our solution is going to be a function u, which depends on both x and t, so space and time. And the domain of our interval is going to be from 0 to L. So physically what you can think of is that we are modeling the temperature of a metal rod with length L. Now the PDE, the equation, is not complete by itself. We are going to discuss this more in the future, but the equation by itself is a lot like a system of linear equations where there are too few equations. We need a few extra conditions in order to really nail down the solution u and get a unique solution. And this is where the boundary conditions and the initial conditions come in. So for the heat equation, the boundary conditions talk about how the heat flows through the two ends of the bar, whereas the initial conditions talk about the temperature of the bar at the beginning of our modeling session. So there are two main types of boundary conditions. There are actually quite a few more, but these two are the ones that are most often used, and certainly the ones that we are really going to see in this class. First, we have what are called Dirichlet boundary conditions. Mathematically, this is where the value of the function is assigned at each boundary. So in this case, a value for u is assigned at x equals 0 and at x equals L. Physically, what this means is that we are fixing the temperature of the bar at both ends. So since the boundary conditions are both set to 0 at either end of the bar, we can think about putting the bar in an ice bath on either end and keeping it at 0 degrees Celsius. The other main type of boundary condition is called a Neumann boundary condition. And mathematically, this is where the derivative of the function is assigned at each boundary. Physically, what this describes is the flux of the heat through both of the ends. Here we have an example where the flux of the temperature is equal to 0 on both ends. And what that represents is a bar that is insulated on both ends. So there is 0 flux. There's no flux throughout the ends of the bar. Now there is a third type of boundary condition, but it's not really a different type, and this is what's called a mixed boundary condition. Mixed boundary conditions occur when both types, Dirichlet and Neumann, occur in a problem, which is certainly allowed. So here we see a solution that is fixed at 20 when at the boundary x equals 0, while the heat flux is fixed at 10 at x equals L. So we have a Dirichlet boundary condition at the one end of the bar and a Neumann boundary condition at the other end of the bar. So just for one more wrinkle, we also have homogeneous and inhomogeneous boundary conditions. So if the value of the boundary condition, either Neumann or Dirichlet, is set to 0, then the condition is called homogeneous. Otherwise, it's called inhomogeneous. So we have a couple of examples here. First, we have an example of an inhomogeneous Dirichlet condition. We have the value of the function at x equals 0 being set to 10, and the value of the function at x equals L being set to 50. So it's Dirichlet since we are setting the value of the function itself, and it's inhomogeneous because we're not setting it to 0. Our second example is an example of a homogeneous mixed boundary condition. It is mixed because we have a Neumann boundary condition at x equals 0 and a Dirichlet boundary condition at x equals L, and it's homogeneous because both of those values are being set to 0. Finally, we have initial conditions. And these are very similar to what you saw as initial conditions in your ODEs class. This sets the value of the solution when time t equals 0. Physically, what this is talking about is the temperature of the rod at the initial time. Now, the main difference between ODEs and PDEs is the value of the initial condition. In ODEs, the value of your initial condition was simply a number. Y of 0 equals 3, y prime of 0 equals 12. However, in PDEs, we are setting the temperature at every point along the bar, so our initial condition is actually going to be a function of x. So this is a very big difference that occurs between PDEs and ODEs. Finally, putting all of this together, we have what is called an initial boundary value problem, or an IBVP. This combines the actual partial differential equation itself with the boundary and initial conditions. So here we have an example of a IBVP with Dirichlet boundary conditions, but certainly another problem could involve Neumann boundary conditions or mixed boundary conditions. So you see that when you actually write down the full initial boundary value problem, it takes up quite a lot of space. There is a lot of information that needs to be conveyed when you are writing down the full problem.